In this video, we're going to take a look at the 2017 iGCSE multiple choice paper 2. And to start off with, what is the most accurate and precise method to measure the thickness of a coin? So we've got a micrometer screw gauge, we've got use a ruler and look at the scale perpendicularly, use a top pan balance and use a displacement method. So we can rule out this C and D straight away because those don't measure thickness, they measure mass and then volume. And that's a common theme with these multiple choice questions. You can often rule out two of the answers straight away anyway. So let's dig into these two. So a micrometer screw gauge is this device here. You'll have probably used it to measure the thickness of wires and things like that. And you'll often talk about looking perpendicular to scales with thermometers and rulers because you're trying to eliminate parallax error. So these are both ways of measuring the thickness, but the most precise method would be using the micrometer because it has a resolution of 0.01 millimeters, so it should be more precise. On Earth, a ball is dropped and falls 2 meters in a vacuum. The acceleration of a ball at 1 meter is 10 meters per second squared. What would the acceleration be at 0.5 meters? Well, if you're in a vacuum, that means there's no drag force, meaning only the weight force is acting. So if we use the equation form of Newton's second law, the resultant force is equal to mass times acceleration. Acceleration is resultant force divided by mass. The only force is the weight force, which is mg. So we can see the mass cancel out, and we just end up with g equals 10. So it doesn't matter what the height is, g is going to be 10. So a skydiver reaches terminal velocity and then opens his parachute. What happens to the skydiver as the parachute opens? Well, there's some nonsensical answers that we can eliminate. The weight of the person isn't changing because they haven't gone to a different planet suddenly. Their speed is going to decrease because you've just opened a parachute. That's the point of a parachute. And there's movement upwards. Nope, you absolutely do not move upwards, despite what it looks like when you see videos of it. So we already think the answer is B. And if you think about it, at terminal velocity, drag equals weight. If you increase the frontal area of the skydiver, the drag force is going to increase. So resultant force is now upwards, and so acceleration is now upwards. So B does make sense. Okay, so a piece of steel is taken from the Earth to the Moon for an experiment. The gravitational field strength on the Moon is smaller than that on the Earth. Which statement about the piece of steel is correct? Okay, so we can already eliminate these first two because the mass of an object doesn't change by taking it to a different planet or a different gravitational field. And the other thing to know is that the stronger a gravitational field is, the larger the weight force is, or conversely, a weaker gravitational field gives you a smaller weight force, so that can eliminate D and leave us with C. Okay, so a measuring cylinder containing only water is placed on an electronic balance. A small irregularly shaped stone is now completely immersed in the water. The diagrams show how the equipment before and after the stone is immersed. Okay, so you can see to start with the volume was 40 and now it's 65, and we can see the mass has changed when we added the stone as well. What is the density? So density is mass divided by volume. So to find the mass of the stone, we need to find the difference between the two mass readings, and to find the volume, we need the difference between the two volume readings, and that gives us our density in grams per centimetre cubed, giving us option C. Okay, so a boat is travelling at steady speed in a straight line across the surface of a lake. Which statement about the boat is correct? Well, we can go straight away to this one because Newton's first law states that an object travelling at constant speed in a straight line has a resultant force of 0. So we know straight away that it's option D. A ball of weight 1.2 newtons drops through the air at terminal velocity. So drag is equal to weight. Okay. So that's going to be the first key thing. So we know that drag is equal to weight, so those two forces are equal and cancel each other out. And they're going to be equal to 1.2 newtons. So sudden gust of wind exerts a force on the ball from the left. Which diagram shows the resultant force while the wind is blowing? So the resultant force is just going to be the force from the wind because the other two forces cancel each other out. So that's going to be 0.5 newtons to the right, and that's shown by diagram C. So the diagram shows a uniform bridge, 4 meters long and weighing 10,000 newtons. The bridge is pivoted at one end, and the force at the other end gradually increases until the bridge begins to lift. Okay, so what I'm going to do first of all is add the force in there we're not showing, show the weight force acting from the centre of the beam. So it's going to be 10,000 newtons from the middle, so 2 meters from the pivot. So if it's just starting to lift, that means the moment clockwise is going to be greater than or equal to the moment going clockwise, because it's actually starting to rotate. And therefore, we know the moment from the lifting force, which is 4 meters from the pivot, must be greater than or equal to the moment of the weight force. And if we rearrange that, we know the force must be greater than or equal to 5,000 newtons. And since the question says it's just beginning to lift, that means we're going to give option B. Okay, so a bullet of mass 0.1 kilograms travels horizontally at a speed of 600 meters per second. It strikes a stationary wooden block of mass 1.9 kilograms resting on a frictionless horizontal surface. A bullet stays in the block. What is the speed of the bullet in the block immediately after the impact? So we're dealing with a collision, so we're going to be using conservation of momentum. That's the principle we use to deal with collisions. And we know what the initial momentum is. It's 0.1 times 600, and the mass of the bullet and block combined would be 2 kilograms because we add their masses together, and we want to find out what the final velocity is. So then we can rearrange it and calculate the velocity as 30, so that's option A. So a box of mass m slides down a slope of length L and vertical height d against a frictional force F. As the box slides down the slope, it loses gravitational potential energy and it does work against the friction. Which row gives the loss in gravitational potential energy and the work done against friction? Okay, so the equations we're going to use, so the work done is force times your displacement in the direction of the force. So the force is acting parallel to the slope, so we need the distance travelled parallel to the slope, which is L, so we're going to do FL. And change in gravitational potential energy is mg delta h, and the change in height is given by d. So we can see, looking through the table, we want option A as our answer. So we've got a Sankey diagram representing energy transfers for a device, and it's 50% efficient, so we've got half is useful and half is wasted. Okay. So remember, efficiency is useful output over input. So essentially half of our energy, as I said, is useful, then half of it is wasted. Okay, so what that means is the input has to be double the useful output because we've wasted half of it. And it also means the wasted is the same as useful. So if we go through our options, input is useful divided by 2. Nope. It's going to be the option C here, where we've got wasted equals output, as we saw earlier. So a student carries out some simple exercises, in which exercise is the most work done. So what I'm going to do is I'm going to calculate the work done in each of the 4 scenarios. So in the first one, we're doing work to increase the gravitational potential energy. So we're going to do the mass times g times the height change. The second one, we're just doing work against friction, so we're going to use work is force times distance to get that. And we're going to repeat the process for C and D, and we can see that C is the one that has the most work, and by quite a long way. Okay, so we've got 4 different liquids in 4 containers. The diagrams show the depth and density of liquid in each container. Which container has the largest pressure on the base? So we're going to use this equation, pressure equals density times gravitational field strength times height of the column of fluid. And what we're going to do is we're going to calculate the pressure in each of the scenarios. So the G has no effect because it's the same in all of them. So the first thing I've done is I've actually converted grams per centimetre cubed into kilograms per metre cubed. And I happen to know that to do that, you times by 1,000. And then I've converted the height into meters as well, and I've done that so we end up with the unit of pascals or newtons per meter squared. You don't actually need to make that conversion at all. Whichever units you use in your calculation, you should still end up with the correct answer, which is C, because it comes out with the biggest number. Brownian motion is observed when using a microscope to look at smoke particles in the air. What causes smoke particles to move at random? Well, it's the smoke particles being hit by air molecules. That's what. And we can observe the smoke particles and we can see that. So gas molecules striking a container wall cause a pressure to be exerted on the wall. Which statement explains this? Okay, so collisions between gas molecules and container are considered to be elastic collisions, which means there's no loss in energy for the gas molecule during the collision, and therefore their speed stays exactly the same. But momentum is a vector, so the direction change means there is a change in momentum. So even though the speed's still the same, momentum has changed. So we can see that we end up with B, and then just to check, option C we just spoke about, and then remember that average speed and temperature are the same, essentially the same thing. So if the speed doesn't change, the temperature hasn't changed either. Equal masses of two different liquids are put into identical beakers. Liquid 1 is heated for 100 seconds, liquid 2 is heated for 200 seconds by heaters of the same power. So we've supplied with the same amount of energy every second. Each liquid has risen by the same temperature. Which statement is correct? So, in terms of energy, the first one had half the amount of energy delivered that the second one has, because we've had the same power for different amounts of time. So the first one has achieved the temperature with a smaller amount of energy. So they can't have the same thermal capacity, because we've supplied a smaller amount of energy and got the same temperature change, and we've got the same mass. Each beaker does not receive the same amount of energy. The second beaker gets twice as much. Again, sigma C doesn't make sense. Liquid 2 receives more energy. So we're left with this last one. The thermal capacity of liquid 1 is less than the thermal capacity of liquid 2, and that makes sense because it's required a smaller amount of energy to change the temperature by the same amount. So water of mass 100 grams at temperature of 100 degrees centigrade is converted to steam at 100 degrees centigrade. The specific latent heat of vaporization of water is 2,300 joules per gram. How much thermal energy is absorbed? So we're going to use this equation, Q equals ml, and we've got the mass in grams and the specific latent heat in joules per gram, so we can just multiply those two directly and get our answer of joules. So a copper bar and a wooden bar are joined, and a piece of paper is wrapped tightly around the join. The bar is heated strongly at the centre for a short time, and the paper goes brown on one side only. Which side goes brown, and what does it show about the wood and copper? So, if we compare their properties, copper has a higher conductivity, and so the paper on top of it doesn't burn because thermal energy is conducted away. So, we need, the brown side is going to be wood because it's an insulator, and the copper, however, is a conductor, so then it's not going to burn. So that gives us D. So different waves hit barriers with different sized gaps. The waves will diffract. In which diagram does the greatest spreading occur? So maximum diffraction happens when the gap size, or the object size, is the same size as the wavelength. So that's going to be B. A converging lens is used as a magnifying glass to view an object. Which statement is correct? Okay, so if we draw a diagram for a converging lens being used as a magnifying glass, the object has to be inside the focal length of the lens, and that leads to it being magnified. And as you can see, the rays converge. Well, they don't actually converge. There's a virtual convergence point. So we're going to get a virtual image, but you can see that the image is upright, so that's not inverted. It's clearly further from the lens, and it's clearly bigger, but it is a virtual because no light rays actually pass through where the image is formed. So which diagram shows what happens when a ray of white light passes through a prism? So there's quite a lot to this, so let's dig into the details behind it first. So, why did they split in the first place? Well, red light travels faster in glass, and so it has a smaller refractive index than violet light does. That's our first key thing to know. And so I'm going to use Snell's law in this form, and all the wavelengths have a refractive index of 1 in a vacuum. So all wavelengths travel at the same speed in a vacuum, and they all have the same angle of incidence at the first boundary. So n1 and sine I are the same for all the wavelengths at the first boundary. So a smaller refractive index gives a larger angle of refraction to equal the same n1 sine I term. Sometimes we describe that as being refracted less. Okay, so going from a vacuum to air, the the rays bend towards the normal and going away from the normal when they go from glass to air, but in both cases they must cross over the normal. Okay, so now let's go through each of these diagrams. So what we should see at the first boundary is the different wavelengths splitting up because they've gone into glass, so Snell's law predicts they should take different angles of refraction. So A doesn't make sense because they haven't been dispersed. B doesn't make sense because they've clearly bent away from the normal instead of bending towards it when they've gone into our higher density medium. That doesn't work. C doesn't work because at the second boundary they haven't crossed over the normal. It looks like they've been kind of reflected off of the normal, if you like. So that doesn't work. So option D must be the correct one. So light travels from a vacuum and enters a glass block. The speed of light in a glass block is 2 × 10 to the 8. Which statement about the speed of light is correct? So we can actually figure out the refractive index, and we can see it's 1.5 because light in a vacuum travels at 3 × 10 to the 8. So the speed in a vacuum is 1.5 times the speed of glass. Yep, that one's correct. Their speeds are the same. Nope. The speed of glass is faster than the vacuum. That's impossible. The speed in glass is 1 × 10 to the 8 times the speed of a vacuum. That doesn't make sense either. You can't travel faster than light in a vacuum. It's impossible. So a fire alarm is not loud enough and the pitch is too low. An engineer adjusts the alarm so that it produces a louder note of higher pitch. What effect does it have on the amplitude and frequency? So higher pitch means higher frequency, higher amplitude means louder. So we're going to need to make both of them bigger. In a child's toy, metal fish are lifted out of a toy pond using a metal rod. The fish are magnetically attracted to the end of the rod, but there's no magnetic force between the fish themselves. So what that tells me is the fish are soft magnetic materials, so they quickly demagnetize if there's no magnet around them, which is why they're not attracted to each other. But the rod must be a permanent magnet and so must be made of a hard magnetic material. That's how it's able to be attracted to the fish. So in terms of our options, so our fish must be made of soft iron and our rod must be made of steel. That's the only one that works. What is the most effective method of demagnetizing a bar magnet? Placing a magnet in a solenoid carrying a large alternating current and gradually decreasing the current. That would definitely work. This is the most effective, so let's check the other options. Place it in a solenoid with a direct current. Nope, that would just magnetize it in a different direction, potentially. Placing the magnet in a solenoid that produces a magnetic field in the opposite direction. No, that would just remagnetize it in the other direction. Placing the magnet next to another bar magnet with its poles in the opposite direction. Nope, they would just attract each other, but they wouldn't demagnetize each other. So A is the most sensible one. A magnet near a coil of wire is attracted to the coil only when there's a current in the coil. Which statement explains this force of attraction? The coil of wire has its own gravitational field. Nope. The force would be too small to be noticeable. The coil of wire is made from a soft iron. Doesn't matter. We're not turning the coil into a magnet by aligning its domains. We're doing it by passing a current through it. The current creates a magnetic field. Yes, that is absolutely true. If you have moving charges, you have a magnetic field around them. A student rubs a plastic rod with a cloth. The rod becomes positively charged. What happens to the rod? Okay. Well, if it's become positively charged, it must have lost electrons because static charge is caused by either gaining or losing them. So if it's positive, it's lost electrons. What quantity is measured in coulombs? That's charge. You just have to know that. A cylinder of conducting putty has length L and diameter D and resistance R. The putty is now moulded into a cylinder of diameter 2D that has the same volume. Okay, so first of all, doubling the diameter causes the area to quadruple, and 4 times the area gives you 1/4 of the resistance. That's the starting one. Quadrupling the area must mean the length has been quartered to keep the same volume, and quartering the length quarters the resistance. So we have quartered the resistance twice, which means we're 1/16 of the original resistance. So the average current during a lightning strike between a cloud and a ground is 1.5 times 10 to the 4 amps. The lightning releases 3 times 10 to the 8 joules of energy and lasts for 2 times 10 to the minus 4 seconds. What's the average EMF between the cloud and the ground? So first of all, I'm going to work out how much charge has been moved. And then using this equation here, which says the energy is equal to the number of charges times by the energy in each charge. So we can then rearrange that to calculate the potential difference, or in this case the EMF, and then get our value of 10 to the 8. A student connects a variable potential divider circuit. Let me see here. What happens to the reading of the voltmeter as the sliding terminal T is moved from R to S? Okay, so when it's connected to R, the potential difference reads 0 because it's not connected across any resistance. And if you're not connected across any resistance, there's no change in energy between the two connections, so you measure nothing. But as you slide towards S, the resistance it's connected across increases, so more energy is removed from each charge between the 2 points, and therefore you get a bigger reading. So it's going to go from 0 to 12. Okay, so the circuit diagram shows a circuit with an AC supply, a diode and a resistor. Which diagram shows the current with time? Well, a diode only allows current in one direction, so it's going to chop off any negative current that you get. So we're going to end up with this one here. We're just going to get nothing during those periods. So this is often referred to as a half-wave rectifier. So a light-dependent resistor and a resistor are connected in a series circuit. Light falls on the LDR. The brightness of the light falling on the LDR decreases. What happens to the resistance of the LDR, and what happens to the reading on the ammeter? Okay, so if it gets darker, the resistance of that LDR is going to increase. So it's got to be C or D, and that's going to cause the current to decrease because we've got a bigger resistance applied across the terminals of the power source. So we can see that it's going to be option C. Diagram shows a logic gate. That is a NAND gate or a not AND gate, which gives a output of 0. So both inputs would have to be 1 so that the output of the AND gate is 1, and therefore when it gets knotted that becomes 0. So it's going to be option D. A simple DC electric motor is fitted with a coil that rotates in a magnetic field. A commutator connects the power supply to the coil. What is the point of a commutator? It converts AC into DC. No, it doesn't. It's there to reverse the direction of current every 180 degrees of rotation. That's in fact the only reason it's there. What is the purpose of a relay? It allows a small current circuit to switch on a large one. So logic gate circuits all run on very low current, but you can use a relay to allow those circuits to control very high-powered, high-current circuits. Which row gives a relative charge of an electron, a neutron, and a proton? So an electron has a relative charge of -1, proton +1, neutron is neutral, so nothing. A nuclide of element X undergoes beta minus decay. Which statement is correct? So during beta minus decay, a neutron turns into a proton, so the number of nucleons hasn't changed. The nucleon number stays the same. Okay, so sample of radioactive isotope is decaying. The nuclei of which atoms will decay first? It's impossible to know because it's completely random. Radioactive decay, nothing is predictable. We can only model it using statistics, so everything is completely random. A detector of ionizing radiation gives a background reading of 20 counts per minute. A radioactive isotope with a half-life of 2 days is brought near to the detector. The reading on the detector increases to 100 counts per minute. How long does it take for the reading on the detector to reach 40 counts per minute? So the first thing we have to do is figure out essentially what is actually going on with the sample itself. So we're going to subtract 20 from both of the readings to tell you what the actual sample is doing. So that's why we've done 100 minus 20 and 40 minus 20. We've got rid of background radiation. And once we've done that, we can see that 2 half-lives have passed. It's gone 80 to 40, 40 to 20, so it's halved twice. So 4 days must have passed, and that completes this multiple choice section.